Hello! Welcome to this video tutorial on the finite volume method, which is a wonderful method and is extensively used in computational fluid dynamics. The finite volume method is commonly abbreviated as FVM. We have already looked at this method for a one-dimensional problem, so today we will look at this method from a more general perspective by looking at two-dimensional problems. We will start with a general approach towards finite volume formulation, but eventually simplify the formulation to apply to Cartesian mesh, which is our current problem at hand. But before we begin, let us look at the advantages that the finite volume method offers compared to other methods. The finite volume method, unlike the finite difference method, is very easy to apply to unstructured mesh. As you will soon see that the finite volume formulation does not depend on any kind of cell shape. This allows the finite volume method to be applied to complicated problems involving complex geometries. Also, extension of the method from 2 dimensions to 3 dimensions is very straightforward. A discretized formula after applying the finite volume method reads like the physical statement itself. A finite volume formula in plain English reads something like this: the amount of stuff entering a volume minus the amount of stuff leaving out from the volume must equal the rate at which the stuff is growing inside the volume. It is as simple as that, and thus has a nice physical intuition to it. Like you can see in this animation, the amount of vehicles entering this piece of road have to leave the road or accumulate over this piece of road. The finite volume formulation allows us to have this kind of an insight and is also therefore easier to debug. The finite volume method implies conservation by design, which means that the finite volume method will not generate or destroy conserved quantities like the mass, momentum, energy, and others alike. This is a very important property as far as fluid flows are concerned, and I believe that this is the most important property of the finite volume method. Looking at the previous example again, it would be spooky if vehicles start appearing or disappearing from the road, isn't it? The finite volume method ensures that such a thing does not happen in simulations. Also, another compelling reason to understand this method is that a lot of CFD software is written using the FVM. And if you want to modify the underlying code, then you must certainly understand the finite volume method. Now, let us have a look at the finite volume formulation. The finite volume formulation has two different flavors. One of them is called the cell vertex method and the other one is called the cell-centered method. The cell vertex method uses a secondary mesh made up of a cell for every vertex. Given a mesh produced by the meshing software, which is shown in black color here, we have to first generate a new cell for every vertex by joining the centroids, which is drawn in a blue color here. The finite volume formulation is applied on these newly generated cells. The advantage of the cell vertex method is that the application of boundary conditions becomes easy because the cell centroids lie on the boundaries. However, the construction of secondary mesh and the data structures associated with it can get a little messy if not handled properly. The second flavor of finite volume method, the cell-centered approach, uses only single mesh made up of a single set of cells. The mesh generated by the meshing software is directly used as cells for applying the finite volume method. This makes the data structure a bit cleaner and convenient to work with. We will be using the cell-centered approach for deriving the finite volume formulation. To derive the finite volume formulation, let us consider this partial differential equation, which is a representative for a general governing equation. This unsteady two-dimensional equation may represent the governing equation for fluid flows, magnetohydrodynamics, shallow water equations, or some other type of physical phenomena. Depending on the governing equation that you are planning to solve, this phi, f, g and s can be scalars or vectors. Integrating the equation over a single cell like the one zoomed in here, we can write the equation as shown. The cell can be of any shape like a triangle, quadrilateral, some other polygonal shape, or even a shape with curved edges. However, integrating over curved edges can be a little tough, and therefore we normally only use shapes with straight edges. Now comes the step of simplification, which leads us to the finite volume formulation. We can simplify the first term by using the average of phi, which is defined as the integral of phi divided by area of the cell. Similarly, the integral of the source term gets simplified by using the definition of average of the source term. The most interesting term here is the area integral of the space derivative terms. These terms get simplified by using the Gauss divergence theorem, which converts the area integrals to line integrals over the closed boundary of the cell. You can think of it as if the lines enclosing the area are opened up and then a line integration is carried out over these lines. In case of three-dimensional problems also, the Gauss divergence theorem can be used, where the volume integrals get converted to surface integrals over the enclosing surfaces of the cell. Unit normal n hat has components nx, ny and possibly nz for 3D cells, which are going to be different for each of the faces, and the unit normal vector points outward of the cell and not inward as per standard convention. We can now split the integrals for each of the faces to obtain this expression, which can be further simplified to obtain this equation using the definition of averages. This is almost the final step of finite volume method. Hereafter, the steps of finite volume method depend on the scheme used for calculation of fluxes and time integration. We will look at the methodology for calculation of flux terms in case of a unstructured mesh later when we deal with unstructured mesh. However, for a Cartesian mesh, as we will see soon, these terms simplify even further to give us equations very similar to the one-dimensional formula for which we have already written a program earlier. That was the finite volume method. Now, let us use it to solve our problem at hand. We are interested in solving the simple 2D advection equation using a simple Cartesian mesh. This equation looks similar to the governing equation for which we have just obtained a finite volume formulation. However, we have these terms ax and ay which are outside the derivative term, unlike the equation we used for deriving the finite volume formulation. This form of partial differential equation is called a non-conservative form, and we cannot use this form for applying the finite volume method. So, we have to first convert this partial differential equation to a conservative form, which can be easily done by substituting f as ax phi and g as ay phi. This moves the constants ax and ay inside the derivative. Now, continuing the procedure of finite volume method as we did earlier, we have a simplified equation where delta x times delta y is the area of this rectangular cell, and since we do not have a source term, the right hand side is 0. When we solved the one-dimensional problem in the previous series of videos, we only had a single term here, but now we have two. So it would be great if we could have a single term here so that we could use our previous code. Well, it turns out that for a Cartesian mesh, it easily simplifies further to a single term inside the line integral. As you can see, for a Cartesian mesh, the vertical faces have ny equal to 0, therefore the term g times ny goes away, and for horizontal faces nx is equal to 0, therefore f and x becomes 0. And therefore we get single terms inside the integral. Simplifying this further by using the average values of flux over the faces, we can get rid of the integral as well. Let us call the right hand side face as I plus half, the left hand side face as I minus half, the top face as j plus half, and the bottom face as j minus half. Now, recognizing the fact that nx is equal to positive 1 for the right face and nx is negative 1 for the left face, similarly ny is positive 1 for the top face and ny is negative for the bottom face, we get this equation. This results in this final ordinary differential equation, which we can solve using the Runge-Kutta time integration method as we did in the one-dimensional case. One final thing which you may have already observed is that this equation looks a lot like the one-dimensional formula, with this additional term for the y direction. So with this we can conclude that the finite volume method for a Cartesian mesh behaves similar to two one-dimensional problems. Therefore, we can go ahead with the same code and make a few modifications in our code to solve two-dimensional problems. I was initially planning to cover the indexing for a two-dimensional Cartesian mesh in this video itself. But since this video is getting too long, let us look at it in the next video, and after that we will start with our code. Thanks for watching through the complete video, which actually has turned out to be a rather long one. If you have any suggestions, feedback or questions, then please leave them in the comment section below. Have a great day and I'll see you next time. Until then, bye bye.